Hello everyone, welcome to our presentation today. So my name is Mazen. I am a PhD student at the Technical University of Clausthal in Germany, and today I will present to you our work on efficient neural network representations for energy data analytics on embedded systems. Okay, so let's start with the motivation behind our work. So the energy consumption of each appliance contains a wealth of information that can be exploited. So for instance, it can be used to develop the intuitions of the residents about the required power to operate each appliance and make comparisons such as comparing a dishwasher to a washing machine, or compare the consumption of different modes in the same device such as eco washing cycle versus heavy washing cycle and so on. And conveying this information through modern familiar methods can have great impact on the influence of the residents and their usage habits. The benefits are not restricted to behavioral aspects of the end consumers, but also include utility companies as well, as they can have better understanding of their users' habits and can thus make educated decisions regarding energy generation and prices. The same goes for other aspects such as energy savings and anomaly detection, which goes hand in hand to identify and prevent the wasteful use of limited energy resources. However, measuring the consumption of each appliance is a hard task, as it requires a measurement device in each electric socket. This is not feasible for end consumers with average expertise with the electrical appliance, aside from other factors such as maintenance and mobility. So to solve this problem of the inability of each resident to measure the electrical consumption in each socket or each device, we can explore the non-intrusive load monitoring approach, which offers a few algorithms to solve this problem by deducing a contribution of each appliance from the total energy consumption of the house. So only with if we have a hold on the total energy consumption of the house, as it's seen here in this blue figure here, which represent the total energy consumption over time. By using one of the NERM algorithms, we may be able to deduce the energy consumption of each appliance on its own over time. So how much is the contribution of the microwave to the total consumption, which here represented orange, for instance, and so on. Modern solutions for the NERM problem are actually based on deep learning and neural networks, especially sequence-based neural network. So they disaggregate a window of samples of the total energy consumption into the consumption of one appliance, on which the neural network has been trained. And especially the sequence-to-point neural network has proven itself as one of the most prominent solutions, as it delivers the best results. And the only difference is that instead of predicting a whole sequence of the energy consumption of a certain appliance, it predicts only the middle point of the appliance, and that's where the name comes from, sequence to point. So it's disaggregate a sequence into a single point, which is the energy consumption of a certain appliance in the middle of that window. However, this model suffers from few shortcomings, especially if we consider a long input window. So as the window gets bigger, usually the prediction quality also get higher to a certain point, but this also results in higher number of parameters. And for instance, in the original version of a sequence-to-point neural network, the size of the network is more than 30 million parameters, and this requires more than 350 megabytes on a disk. This in turn also influences the inference speed, which is much longer, compared to smaller models, which offer the opportunity not only to save them in smaller systems and they need less power and less memory, but they also, if they are small enough, we can employ them on embedded system, for instance, and allow the end consumers to process their data directly, which eliminate a lot of privacy concerns in this regard. So why using embedded systems? First of all, they are cheap to obtain. And second reason is privacy, especially in the case of NERM. So many private aspects about the residents' lives, such as their daily habits and emotional state, can be revealed by exploring the usage pattern of their devices. So ensuring that this data can be processed locally without the need for uploading it to the cloud, eliminate the privacy risk, and save on bandwidth required for real-time power and energy readings. So microcontrollers offer a suitable platform as they are accessible. New hardware iterations and networking solutions also offer more options to ease integration into established home networks such as Wi-Fi and Zigbee. So this leads us to the main focus of this work, which is to optimize the sequence-to-point model in both dimensions, size and accuracy, simultaneously. And for our testing, we deployed the final model using TensorFlow Lite on an ESP32, which is a popular microcontroller produced by Espressif Systems. It has many communication options such as Bluetooth Low Energy, Wi-Fi, 32-bit dual-core processor, and 4 megabytes integrated SPI flash memory. And the SP32 is not optimized for electricity meter applications. For instance, the built-in analog digital converter doesn't have a high enough resolution, but it's more capable than most microcontrollers in the next generation of smart meters. And there is already energy meter that make use of it, such as the expandable 6-channel energy meter from Circuit Setup. So to achieve this goal, we tested different compression techniques for neural networks with custom modification. Unlike file compression techniques, neural network compression is not lossless, but try to make the network faster and smaller in terms of the required memory to operate or store space, usually at the cost of accuracy. Based on our research, we decided to examine the effect of these techniques listed on the slide. And in the next slides, we will go over each compression method on its own and present its result directly as applied to our baseline sequence-to-point model. Finally, we create a single model that combines the best of these techniques and test it on the ESP32. As our goal is to optimize two aspects of the model, namely size and performance, two corresponding kinds of metrics to quantify this aspect have been used. So first of all, the model performance or accuracy, which refers to the quality of prediction and how far away it's from the ground truth. And to evaluate the performance, we choose the mean absolute error, MAE, which is a simple metric to measure the gap between the ground truth data and the model prediction, and gives a good overview of the model accuracy in a single figure and have been used also in many previous studies in the NERM community. The second category is the size, which refers to general properties regarding the model actual storage size, as well as memory requirements and inference speed. And to quantify this aspect, we use the model storage size with results from two parts: a fixed part, which reflect the model architecture and hyperparameters such as number of neurons, number of layers, and so on, and a variable part, which is the weights and biases usually. And the second method or figure that we choose to measure the size is sparsity, which refers to the ratio of the model parameters below a certain threshold epsilon, which is usually a very small positive number. And the sparsity is a good measure to compare some of the compression techniques, as some methods derive the network parameters to values near zero without actually removing them from the model. So two models may have the same size but different sparsity ratios, which make the model with the higher sparsity more prone to compression. Most of the presented compression techniques can be applied selectively based on some categorization of the model parameters. And two popular categorizations are the parameters types, either learned during training, so static, weights and biases, or variable. And by the location within the network, and in convolutional networks, there's usually a distinction between the parameters that represent the learned filters and the initial convolutional part of the network, and the rest of the parameters that produce the final output and the fully connected dense part of the network. And we may want also to avoid heavy compression to important parameters in the network. Thus, we need a measurement to estimate the importance of these parameters. One way to do this is randomization robustness, which is a simple measure to quantify the role of each layer in the network. And the idea is pretty simple actually. So after training the network, we set the weights of a certain layer to its initial values before training, which is usually selected randomly, and measure the degradation in the model performance. So important layers would cause the highest drop in performance and may be unsuitable target for compression. And this measurement is represented here to the right. So provide the results for the robustness estimation for the used baseline sequence-to-point model, which has been individually trained to recognize one of 4 appliance types: microwave, fridge, washing machine, and the dishwasher. And while the last convolutional layer has greater impact on the overall performance than previous layers, the dense layers clearly have the greatest effect on the final model performance, with more than 99% of the parameters. And the result of our study demonstrated that accuracy reductions have great impact in the layers buried deep within the network, so the dense layers here, while the first layers are comparably insensitive to variations. We exploit this knowledge afterwards in our selection of suitable location for applying compression techniques, as we will show shortly. Okay, so now we start with explaining the first compression technique that we used in our study, which is pruning. And pruning is actually pretty simple in idea. So if we have a trained network with some weights value below a certain threshold epsilon, then applying pruning just eliminate these weights by setting their values to 0. And the idea to use weights is because usually weights with small values have lower effect on the neuron output, and pruning marks out such weights by setting their values to 0. However, models produced with one-shot pruning are usually suffer from low accuracy. That's why we may apply iterative pruning, which refers to the procedure of applying multiple successive iterations of training and pruning, thus allowing the model to adapt to the pruned weights and its new structure. And note in both cases that the model size remains fixed actually after pruning, just some of the weights value have been set to 0. Iterative pruning suffers from being pretty expensive procedure because it requires multiple full training iterations. And to solve this problem, we may use scheduled pruning. So scheduled pruning, we can apply pruning during a single training iteration or training duration. So we can split the training phase into 3 phases. The initial part, so the first phase here, where we let the model learn the initial weights value. And then second phase, we apply pruning gradually, as we can see here, until the certain sparsity level has been reached. And the last phase, we let the model heal from this pruning procedure and adapt its structure to the masked out connections. So we can say that we applied iterative pruning just within one single training epoch. This procedure requires a definition of hyperparameters to determine the boundary of each phase and the frequency of pruning and its shape, so linear or polynomial, for instance. So these are the drawbacks that we need to define these parameters in advance. Okay, as pruning on its own doesn't lead to reduction in model size but only increases its sparsity, we can solve this problem by using structural pruning, which eliminates weights with 0 values. This requires understanding of how each parameter value is generated in the weight matrix, which may be in some cases complicated, as tracing back the weight through the network structure and different layers types may be necessary, especially in the convolutional dense transition in the network, for instance. Okay, so here are the results of applying pruning. So we tested iterative pruning with 2 different schedulers, constant schedule and polynomial schedule. And the results here are actually pretty awesome because we didn't only reduce the model size, as you can see here to the right, but we also increased the model accuracy by achieving lower mean absolute error. And this is not unheard of in the community because there's this idea, there's also this paper called the lottery ticket hypothesis, that each network, actually, especially it has a lot of parameter, is over-parameterized. There's a subnetwork that can, without this noise of the original network, can achieve better performance. And one way to reveal this subnetwork is by applying pruning. So yeah, as we can see here, we improved in the case of the const models. The mean absolute error is improved by about 30% from 13.5 watts to about 10 watts. And in the case of polynomial pruning, the results were even better, which we can be explained by the better alignment between the scheduler and the model adaptive learning rate, which is also polynomial. And it's also worth noting that the structural pruning didn't affect the model performance and reduced the model size by about 50%, as we can see here. So applying structural pruning after applying the usual pruning procedure also reduced the model size at almost no cost to accuracy. So the second neural network compression method that we tried out was weight sharing. And weight sharing cluster weights in each layer into a specific number of groups. First centroid are determined and each weight then is grouped into the cluster with the minimum distance to its centroid. As the majority of the sequence-to-point model weights are located in the dense part of the network, we also tried to restrict the application of weight sharing to this dense part of the network in the hope that the unaffected convolutional part maintains the model performance. So different methods can be used to choose the centroids, and these methods have a huge effect on the final model performance. For instance, the linear clustering divides the range between the minimum and the maximum weight values equally. On the other hand, the density-based method ensures that the number of weights in each group is equal. And as we mentioned before, since the weight values actually can be considered as a measurement of the importance of this weight, so we may expect that linear centroid selection method may deliver better results than the density method, which treat weights equally, regardless of their value. And here are the results for the tested models. So we tested each centroid selection method on the full model, prefixed by all here, and the dense part only prefixed by dense. And in general, the density based method deliver poor results as we expected. So in this method, larger weights are treated equally as small weights. However, larger weights are considered more important, as we discussed earlier in pruning, and thus their role vanishes in this method, which could explain these poor results. Both linear and k-mean ++ method delivered better results, so they didn't suffer from this effect, and a produced model with average MEE better than the baseline model, which is also good news. Finally, the random method delivers acceptable results, but only if applied to the full network. So if applied to the dense part of the network, the degradation in the middle performance is more than 2 watts. And regarding the model size, so on average, the models produced were about third size of the baseline model, and also the applying weight sharing to only the dense part of the network didn't result in much higher models. So the next method that we tried out was pooling, and pooling is a popular technique used in traditional neural networks, convolutional neural networks, to reduce the size of the input and maintain manageable number of parameters in the convolutional layers. So in the case of the sequence-to-point model, the majority of the learnable model parameters results from the transition from the convolutional part in the network, so this part here, to the dense part of the network, as each parameter in the final convolutional layer must be flattened for the fully connected layer. Thus, applying pooling at this gap is expected to be most effective in terms of reduction of the number of parameters. However, it's also dangerous as it affects about 99% of the model parameters in one shot. Here's a simple example to visualize a different pooling setting that we tested for the last convolutional layer. So for the full setting here, in this simple example, the layer has 4 filters, each of size 6. And here, global average pooling is applied on all parameters, and the average is computed to a single neuron. For the XY settings, where X and Y stands for different numbers, the average is computed across multiple filters. And the rationality behind this choice here is to attempt to exploit repeated patterns across adjacent filters, as they tend to capture similar features in the inputs. Okay, on this slide, the results of the best XY models are shown, as the full model delivered pretty poor results, so we eliminated here for clarity. And we can clearly identify a correlation here between the model size and their mean absolute error, which is reasonable as larger models have more parameters and thus more expressive power. Still, none of the models was able to beat the baseline model in terms of mean absolute error, as we saw in the previous techniques. The next technique that we tried out is quantization, which refers to the process of reducing the bit accuracy of the model parameters. And this can be done by each layer selectively, but it's most effective if done by the other consideration of the model parameters and rather by their type, so weights, activations, input, outputs, and so on. And for this technique, we tested 4 different settings. Weights 8, which refer to the reduction of the weights precision to 8-bit integers. Mixed 8 and mixed 16. In mixed 8, it was a complicated setting actually. We reduced the precision of weight, activation, and places differently. And in mixed 16, we reduced the precision of the weights to 16-bit floating point numbers. And finally, full 8, in which the precision of all parameters was reduced to 8-bit integers. However, the results of this model was actually pretty poor. Therefore, we eliminate here from the charts for clarity. And as we can see here, in the case of the mixed 16, quantization reduction of the original baseline model size of about 368 megabytes to about 61 megabytes is possible with a slight drop in performance, so from 13.52 to 13.93 watts, which is pretty good. And when using any of the other quantization methods, a further size reduction to 30 megabytes is achieved, however, at the cost of the model accuracy, as we can see here. So in this case, weights 8 delivered the better result than the other mixed 8 technique with about 17 watts mean absolute error. The next technique that we used is depth-wise separable convolutional, which actually pretty great idea that was applied previously to other convolutional neural networks successfully, especially in the case of mobile nets. And it's actually, the idea is actually to reduce the receptive field of the convolutional layer by separating the traditional convolution operation into one-by-one depth-wise filters and merge them together afterwards with point-wise convolutional. And with this technique, we actually achieved the greatest reduction in model size from about 368 megabytes to about 1 megabyte. So about 360 times smaller models. And the ME only increased by about 2 watts, as we can see here. So this idea was pretty simple, by just replacing this convolutional part of the network by another type of convolutional, but it led to the greatest reduction in the model size. The final technique that we tried is multitask learning, which is inspired by transfer learning. Until now, a new model must be trained for each target appliance. However, the initial part of the network captures aspects about the power traces which are applicable for any appliance, such as state switches and peaks. We can exploit this fact by training a single model that shares this initial part among all target appliances and only branch the final layer into different end nodes for each appliance. Using this technique, we created a single model for all 4 appliances that we considered, and the model size increased slightly, as you can see here, as only the final layer is replicated for each appliance, which contains only 1 neuron and 1025 parameters. On the other hand, the ME increased by about 1 watt. We also tested the setting with depthwise separal convolution and compressed the model to about 3 megabytes with an average mean absolute error of 17 watts. Finally, we combined the best techniques into a single model with the compression setting shown on this slide and tested it on the ESP32 microcontroller that we described at the start of the presentation. So the model improves the ME by about 2 watts on average, with a size of around 150 kilobytes for each appliance. And with such model size, there is no need to apply multitask learning to train a single model for all appliances, as with less than 1 megabyte of memory, we can fit more than 6 models, each trained for a single appliance. And the figure to the right here shows the reduction of such models for each appliance. And it's worth noting how the model tend to reduce simpler shapes, as seen in the prediction of the dishwasher, which can be explained by the reduced number of parameters of the model and thus its expressive power, but it was still able to achieve better accuracy overall. In summary, the experiment in this paper showed that it's not only possible to compress a state-of-the-art NIL model for microcontroller, but also to improve its performance along the way. So each marker on the scatter plot here represents the compression method, and the average or the best mean absolute error along the x-axis, and along the y-axis the size in megabytes. So as we can see, the pruning and weight sharing are recommended for any requirements, as they improve the mean absolute error and reduce the model size at the same time. Pooling comes as a close second, and if we need further reduction in size, we can apply quantization and depthwise convolutional while trading performance. Finally, multitask learning can be applied if the number of parameters or appliances is pretty big. So thanks a lot for your attention, and here are the references for this presentation.